Hey, so welcome back everybody to today's session of the Cardiff Analysis Seminar after the bank holiday weekend. It's a great pleasure today to introduce Jean-Claude Cuenin from Loughborough University, who will talk about, who will give a talk titled From Spectral Cluster to Resolvent Bounds and Compact Manifolds. So thank you very much for accepting our invitation, and over to you.
Thank you very much, Matteo, and thank you for the invitation to speak in this seminar. Yeah, I'm going to talk about spectral cluster and resolvent bounds. You can disregard the compact manifolds if you don't like it. So what I'm going to say is applicable in a more general setting, but I'd like to illustrate it in this context because it's most interesting in that situation. So what I'm going to be talking about are two kinds of estimates. So two types of bounds. Okay, and the first bound is the spectral cluster bound. Let me tell you what I mean by a spectral cluster. So a spectral cluster for me is just a sum of eigenfunctions of the Laplacian or Laplace-Beltrami operator corresponding to eigenvalues in a window of length 1. Okay, so more precisely, I'm going to denote by pi lambda the spectral projection of the Laplacian, or I like to write here square root of minus Laplacian, right? So I'm taking the point of view of an analyst, of course, and my Laplacian is negative. So I can take the square root of minus Laplacian just by the spectral theorem. And I'm going to look at clusters of length 1. Or I should say frequency 1, because if you look at actual eigenvalues, the eigenvalues would be between lambda squared and lambda plus 1 squared. So the spacing in energy would be of order lambda. Okay. So if you don't like this notation, you could also think of pi lambda applied to a function f to be just a sum of eigenfunctions with coefficients, just the inner product of f with an eigenfunction phi j, and I take phi j's between lambda j between lambda and lambda plus 1. Okay, and the phi j's are eigenfunctions, so minus Laplace Beltrami applied to phi j here is lambda j squared by j, and of course the lambda j's are an increasing sequence of frequencies going to plus infinity when j goes to infinity. All right, so I'm looking at the Laplace-Beltrami operator on a compact manifold. So I have just this purely discrete spectrum, and I can look at these spectral clusters. You can also just take one eigenfunction, right? One eigenfunction is also possible, but the result is applicable for this more general spectral clusters. And the type of estimate that I'm interested in is, so it's an estimate from L2 to some LQ on the manifold, right? So if you think about eigenfunctions, we think of them as always being normalized in L2, so they have L2 norm 1, right? And of course, this spectral projection has L2 norm equal to 1 because it's an orthogonal projection. So we are interested in Qs which are bigger than 2. And we're interested in bounds of the form lambda to some power. And this power, of course, will depend on Q. And what I mean by this notation here, so this means, let's say this is 2 plus absolute value of lambda. Okay, I'm interested in large lambda, so I will not worry about lambda of order 1. I will always assume that lambda is sufficiently large, but just to be safe, if I forget to write this, I introduce this notation. right? And I write a 2 there because sometimes I'd like to take a log of this, and I don't want to take a log of 1 because this is 0. So it's just a notation. All right, so we'll always be interested in large lambda. So the high frequency limit. Okay, and then the other type of estimate is the resolvent estimate. So of course, everybody knows what the resolvent is, but I'm going to introduce a notation that is convenient here, as slightly non-standard notation. So I denote R of lambda to be the resolvent of Laplace Beltrami operator. So I mean, it doesn't matter. I can write a plus here, or I can write a minus, but they have to have the same sign. Let me write a minus here. Okay, so that's that's what I mean by R of lambda. And so if we draw a picture in the spectral plane, right? So Z, the spectral parameter is lambda plus I squared. This square is standard in this business because we like to think of lambda as a frequency, and when we do semi-classical analysis, we localize in frequency, and then basically one derivative is the same as 1 power of lambda. That's why I like to have a square there. But so if we look at this, if we have the spectral plane, we are interested in a region where, so the real part of Z is basically approximately lambda squared, and the imaginary part of Z is approximately lambda. Right? It's 2 lambda, but I don't care about constants here. And so so I'm interested in estimates that are outside of some parabolic region. And so all the resolvent estimates, they're going to live here. Okay. I could write this in the general case. I could replace lambda plus I squared by Z and take my Z in this region. But it turns out that if you can control the resolvent on the boundary of this region, which is exactly what is written here, then you can use something. You can use some complex analysis on the level of the Fragment-Lindelöf maximum principle to get everything in the blue region. So I'm just going to focus on this spectral parameter. Okay, and so the bounds I'm looking for, now these are LQ prime LQ bounds. Okay, and they're going to be of the form lambda to twice this power sigma minus 1. So that's just a natural analog of this spectral cluster estimate. So if we have sigma here, we should have this exponent for the resolvent. And this is easy to understand. I'm going to explain this. Okay, so now what is this talk about? It's about the relationship between these two estimates. Okay, and it is known and also not difficult to show that.
Sorry, Jean-Claude. May I ask a question? So here Q prime is the conjugate exponent to Q, am I right?
That's right, yes. Q prime is the Hölder conjugate. 1 over Q plus 1 over Q prime is 1. Okay, so it's known that the resolvent estimate is stronger, or implies the spectral cluster estimate. And let me give an argument for that. The argument is very simple. Namely, if we look at the resolvent, so 1 over, now I just replace, so at the end I'm going to replace tau by minus square root of minus Laplace, and I'm just going to use the spectral theorem for that. So tau squared minus lambda plus I squared, if I take this and I take just the imaginary part of that, right? So if if I can bound the whole resolvent, then in particular, I can bound the imaginary part. And the imaginary part is just about, if you do the arithmetic here, it's just about lambda divided by tau squared minus lambda squared plus lambda squared. And so this is approximately 1 over lambda if tau is between lambda and lambda plus 1, right? If tau is between lambda and lambda plus 1, then this factor is of the same magnitude as this factor. Okay, and so if we have this this pointwise estimate, so we can bound the spectral projector from above by the imaginary part of the resolvent, then it's believable that the resolvent estimate would imply the spectral cluster estimate. And actually, what you have to do is you have to use something called the TT star argument. I don't know if this is very familiar, but I'm just going to quickly explain what this means. So TT star arguments, they're very common in harmonic analysis. And basically what it means is that if you have an operator T, which acts, let's say, from some Hilbert space to some Banach space X, right? And it's important that H is a Hilbert space because it has to be self-dual. If you take this, then its norm is the same as the norm of the adjoint T star, which goes from X star to H, because H is self-dual. And then sort of the most useful version of this is the TT star version, so let's square these here. It's still the same. And this is equal to TT star with norm from X star to X. Okay, so that's the TT star method, if you want. Okay, so if you have an operator which acts from some Hilbert space H to some Banach space X, you can convert bounds to bounds from X star to X, and these are usually easier to handle. They're more symmetric in some way. Okay, so here we're just going to take H to be L2 and X to be LQ of the manifold, and then X star is just LQ prime. Right, and the operators we are dealing with, so that these specific T's in our case, they're also very convenient, right? T is either the spectral projection operator pi lambda, and then T star is just T because it's an orthogonal projection, and also T star T or TT star is the same as T. So they're all the same. And for the resolvent, let's say, let's write it like this. We have just T star, it's just the resolvent, but with set complex conjugate instead, and TT star is the product of resolvents, and then you can use the resolvent formula, and it gives you basically 2 times the imagine. Maybe there is a sign there, I'm not sure, but never mind. The inverse of that, then the difference between the resolvents. Right, so TT star are very easy in our situation. They're explicit. All right. So what's the aim of this talk? The aim of this talk is to explain how the converse is true, or when the converse is true. Right, so I'm going to argue that actually the resolvent estimate is only putatively more general. In fact, it's completely equivalent to spectral cluster bound. All right, and this simplifies a lot of things that have been done in the literature people have started to prove resolvent estimates, and there are at least 5 papers I know that prove the sort of standard resolvent estimate on compact manifolds that use different proofs, but none of them exploit the spectral cluster estimate to the fullest. And so if you use that, then it's immediate. You don't have to do anything. And so these papers are quite, I mean, usually this is quite hardcore harmonic analysis. What you have to do, you have to construct parametrices by various methods. The different parametrices that you can use depending on the smoothness of your coefficients, and then you have to prove estimates. And so usually the point of view that people have taken so far is you just redo everything that you have done for the spectral cluster for the resolvent, and then you have to go through 100 estimates and check where you have to adjust something. And so I was trying to do that in a specific case. I was trying to prove resolvent estimates for manifolds with boundary, and there is a corresponding result of Smith and Sock that I'm going to mention later, which contains the result for a spectral cluster estimate. And I was trying to go through these inequalities, and as it is in harmonic analysis, usually people split things in infinitely many pieces, and they estimate every piece by different methods and so on. You very quickly get lost in all these decompositions and estimates. So I try to find sort of a more robust way to do this. All right, so there's a naive way to do it, and I'm going to show it to you. And it's not going to work. It's going to give us a result which is almost what we want, but not quite. So we'll have to improve it later. Okay, and the naive attempt is just, so you write your resolvent, you just write the Fourier series. So the coefficient is, so this is 1 over lambda j squared minus lambda plus I squared. And then you take the spectral projection corresponding to lambda j, and you sum over all j. Right, so that's what the resolvent is. Right, so these EJs, these are the projections corresponding to lambda j. So all the eigenfunctions phi j with the same eigenvalue lambda j. But in this way, it's if I write it for the projections, it's unique as opposed to the so the projections are unique, but the eigenfunctions are not. That's why I'd like to write it like this. And then you can do something, and I'm not going to be very precise here, but this can easily be made precise. You can replace the spectral projections corresponding to lambda j by these unit band spectral clusters. So pi k. Remember that pi k is the projection that projects onto frequencies between k and k plus 1. Okay, and then you sum over all the k's. And the reason why you can do this is if you look at this denominator, this is approximately constant on the unit scale. So if you shift your lambda j between k and k plus 1, then it's going to differ very little. So I can just replace it by any point in this interval, let's say by k. Okay. So as I said, this can be made rigorous, but for the purpose of this exposition, it's enough to just do this. And now we just do the triangle inequality, right? We just estimate what is R of lambda. And from now on, I'm going to write Q prime Q as an abbreviation for LQ prime to LQ of M. And so if I do the triangle inequality, then what I get is, so I get the LQ prime LQ norm of the pi k. And if you go back to what I said about the TT star, so TT star is T for the spectral projection, right? This was this here. So, so actually, you can formulate the spectral projection bound in a TT star way, and you can convert the L2 LQ to an LQ prime LQ norm. And what you have to do is you just have to square the right-hand side. So you have lambda to the 2 sigma q here. And then you have to divide it by whatever this denominator gives you. And it just gives you roughly k squared minus lambda squared plus lambda. If you separate the real part and the imaginary part, then that's roughly what it is. And
can I ask a quick question?
Yes.
So you defined your projection pi k to be projection onto the closed interval. So
yes, between
do you care if you have something on the edge of this interval on if you
no,
have
no, I
eigenvalue?
don't. No, I don't care about that.
Because you'd count it twice.
I count it twice because I don't care about constants, basically. All right. So if you look at this sum, then in general, I didn't tell you what sigma q is, but sigma q is going to be something non-negative, and in general, this will be divergent. So you don't get what you want here. But if you look at an individual term, and okay, so what you can do is you can insert here a projection to frequencies, let's say less than 2 lambda, right? And then you make this convergent. So here you only look at k bounded by 2 lambda. And the reason you can do this is that the complementary part, so if you project to frequencies bigger than lambda, then you are already away from the characteristic set, right? Your resolvent is basically minus Laplace minus lambda squared. All right, so if you have frequencies bigger than 2 lambda, then your operator is going to be elliptic. And if you have an elliptic operator, then everything is, in this situation, everything is trivial. You just do Sobolev embedding. So you can really reduce yourself to this characteristic set here. And if you do this, then what you will find.
Sorry, may I just follow up quickly on Jonathan's question? So do you really count them twice, or do you exclude them somehow at this point? So say if you have that at this point you have clusters of eigenvalues, that multiplicity grows very fast as you go to k plus infinity, wouldn't this create a problem, or would this still be okay? So you might be particularly unlucky and your operator might have very large eigenspace at these points.
You know, this is, in any case, is more a caricature than what I really do. And you know, what you really do is you take a smooth cutoff function, for example, and then they have overlap anyway.
Mm-hmm.
So that's why I didn't think of you know, whether they overlap at the edges. It doesn't matter. Okay. It gives you some constant. Okay, so when k is less than 2 lambda, then you know, this thing here is basically, this is k minus lambda, k plus lambda, but k plus lambda is approximately lambda in this regime. Okay, so what you have is you have an overall 1 over lambda, and this what you get is what you want. It's lambda to the 2 sigma minus 1, but then you have to sum this this remaining term, which is basically 1 over k from 1 to lambda, and this gives you a log. Right, so this gives you this logarithmic divergence, and it's just a log, so it's not terrible. But on the other hand, people in this business work very hard to improve things by log. So you don't want to lose logs, right? I mean, what I'm going to say is also going to be applicable to so-called improved estimates. If you have certain geometric or dynamical assumptions on your manifold, you can cut down your estimates by, for example, by a log of lambda. So if you have this improvement, you don't want to lose it because of this inefficient use of the triangle inequality. Okay, so we're going to get rid of this log lambda. All right, so just a comment. What if we had considered something different than the resolvent? For example, the resolvent to a power strictly bigger than 1, then everything would have been fine, right? This logarithmic divergence just comes from the fact that the resolvent gives us this 1 over k in the denominator. So if we had a power strictly bigger than 1, we would have 1 over k, let's say, to the power 1 plus epsilon, and this would be absolutely summable, and we would get the sharp result. But for the resolvent itself, it doesn't work. So we need to somehow exploit a certain amount of cancellations in this sum. This result tells us that we haven't used cancellations properly, probably, because the triangle inequality loses this logarithm. All right. Okay, so before I'm going to do this, let me tell you a bit about spectral cluster bounds. What is known? And I'm going to start with an example that some of you have probably seen. So this is the example where M is just a 2-sphere. And so I'm going to illustrate sort of the 2 possible regimes of concentration that you can have in these spectral cluster bounds, right? So there's going to be one region of Qs for which the first example gives you the worst possible behavior, and another region of Q where the second example gives you the worst possible behavior. And the examples are very simple, right? So on the sphere, all your eigenfunctions are just spherical harmonics. And so there is one special spherical harmonic called the zonal spherical harmonics, and you can place it wherever you want, say at the poles. So, and it's going to be large pointwise in the neighborhood of the poles. And since we are in 2 dimensions, the scales are, so the width of this thing is approximately 1 over lambda, and the height of this is approximately square root of lambda. Okay, so if you sit down and compute the Alkene norms, let's say phi lambda is this zonal spherical harmonic, then what you do is you just, it's just base times height, right? It's, what is the base? The base is lambda to the -1. So it's lambda to the minus dimension, which is 2 divided by Q. That's what you get from the Alkene norm. And then the height is 1/2. Okay, that's the Alkene norm of this eigenfunction. And then you have another example, which is the highest weight spherical harmonic, and the highest weight eigenfunctions, they're concentrated on the geodesic. So they're large here, but they're very small outside. So they're Gaussians basically, and they're not completely zero away from the geodesic, but they decay like a Gaussian away from this scale. So the scale is lambda to the -1/2. That's the thickness of this tubular neighborhood of the geodesic, and their size is basically lambda to the 1/4. Okay, so everything I'm saying is of course true in higher dimensions. I'm just doing this in 2 dimensions because it's simpler. All right, so what's the Alkene norm in this case? Again, it's base times height, but now you have to be careful. Base, it's the lambda to the -1/2 should be taken to the power 1, because it's just the size in the transversal direction. If you go in the longitudinal direction along the geodesic, then the thing has size 1. Okay, so it's 1 times lambda to the -1/2, and then divided by Q. So this gives you, and then plus the size, plus 1/4. All right, and now you can compare these 2 guys and see when one becomes bigger than the other, and you find that the point of transition will be Q equal to 6. Okay, so there is a sort of a phase transition at Q equal to 6, where one regime becomes worse than the other in terms of concentration. Okay, and incidentally, if you know about sort of Strickhart's estimates or Stein-Thomas, then Q equals 6 in 2 dimensions is a very very famous exponent. It's exactly what you have for Strickard's estimates or for the Stein-Thomas theorem. So in higher dimensions, Q would be 2 times n minus 1 divided by n plus 1. All right. Oh, sorry, that's not correct. Sorry. It's the other way around. Like this. All right. Okay, and so what is known, what Sock proved in the 80s, is that the spectral cluster bound holds for all Q between 2 and infinity on any compact manifold. And it's sharp. So basically, you can transplant these examples on the sphere. The examples on the sphere can be shown to be sharp. You can transplant these examples to any compact manifolds, to any compact manifold. And so a picture, so if you have your exponent here and you have 1 over Q here, so then the relevant range would be between 0 and 1/2, right? Q equal to 2 is the trivial estimate. So you have sigma equal to 0 because the L2 norm is 1. And the L infinity estimate gives you lambda to the 1/2. That's the size of the zonal spherical harmonic. And then there is this exponent 1/6 or Q equal to 6, which gives you the phase transition. And basically, you have one kind of estimate here and another kind of estimate here. Right? And here you would have lambda to the 1/4, as we saw. So this part corresponds to the zonal function. And oops. Okay, that was not intended. This part here corresponds to the highest weight spherical harmonic. And this picture is true on any manifold, not just on the sphere. All right. Of course, if you have another manifold, then possibly you could have better estimates for individual eigenfunctions, but you can never have better estimates for these spectral projections of length 1. So for these, it's completely sharp. But improvements are possible for single eigenfunctions. And this requires certain geometric or dynamical conditions. So this is the analog of the Doistrumat-Guillemin theorem, for example, saying that you can improve the Weil law from big O to little o, the remainder in the Weil law from big O to little o, if you have if your set of periodic geodesics has measure 0. So statements of this sort are also true for these LP norms. Okay, and then what I'm more interested in actually here is the opposite. So when you have losses, possibly. So you could have losses in the spectral cluster estimates if your manifold is very rough. So if you have only if you have a rough metric, say only G1 or something like that. And related to this is the case where you have a manifold with boundary. I'm going to explain this. So Smith and Sock proved sharp estimates in 2 dimensions for manifolds with boundary. Okay, and the proof, I mean, they have results in higher dimensions, but they are not sharp. They don't give the, I mean, there are sort of counterexamples that tell you what the sharp estimates should be in higher dimensions, and in higher dimensions this doesn't match these counterexamples. So, but in 2 dimensions, the picture is the following. Again, if you have your exponent sigma here and you have 1 over q here you have the trivial estimate, and remember here we had this q equal to 6, which was critical in 2D. But now what happens, okay, let me draw the previous situation. So we had something like this here. Okay, but now what happens when you have a boundary is that you have a new phase transition, which happens at q equal to 8. Right, so q equal to 8 is the new interesting exponent, no longer q equal to 6. And what happens is that up to q equal to 8, you have perfect estimates, just like in the case without boundary, and then you get worse, and you have to interpolate between this and this, and it's sharp. So the red line is also sharp. And the example comes from the PhD thesis of Grieser, and it's basically the whispering gallery mode. So you look at the disk. So this is Grieser's example from his PhD thesis. You look at these whispering gallery modes. So these are eigenfunctions which are highly concentrated near the boundary. So they have multiple reflections, and they sort of creep along the boundary. Okay, I can not draw it very well, but you get what I mean. So, and now this is the worst counterexample that is responsible for this new exponent q equal to 8. Okay, and so now I'm going to explain how Smith and Sock proved these, just looking at this example here of the disk. So if I look at the disk, my Laplacian in polar coordinates is dr squared plus 1 over r squared d theta squared. And now I change variables. So let me call theta x1, and let me call r 1 over 1 minus x2. So x2 is the boundary defining variable. x2 equals 0 defines the boundary. So in these coordinates, this is written as dx2 squared plus 1 over 1 minus x2 squared dx1 squared. Okay, and now what you can do, now you have sort of straightened out the boundary, and you can just extend your eigenfunction. I mean, if you have a boundary, you need to specify a boundary condition. So if you have a Dirichlet boundary condition, then your eigenfunction has to be zero at the origin. So this is x2 here. So here is the manifold, and the left-hand side is sort of the double of the manifold, and we just extend the eigenfunction in an odd way. So this corresponds to Dirichlet. And of course, if we have a Neumann boundary condition, we would do it in an even way. Okay, and so now we have doubled the manifold, and of course we need to extend the metric across the boundary, and we need to do this in an even way. So we need to replace x2 here by the modulus of x2 here, and then you see what happens is that we end up with a Lipschitz metric. So we have removed the boundary, but we have a Lipschitz metric. Okay, and Smith and Sock, they proved their estimates actually for operators that have coefficients of this type. So they are Lipschitz across the boundary, across a hypersurface. And that's sort of fortunate for me because my resolvent estimates, in general, they don't work on a manifold with boundary. You cannot convert the spectral cluster estimate to a resolvent estimate if you have a boundary, because so if you know about pseudo-differential operators, when you have an operator with which is of, I mean, what I do works for operators called principal type operators. But if you have a boundary, then you have points on the boundary which are called glancing, and at these points, the sort of this microlocal thing doesn't work. So, but if you can reduce it to a case where you don't have a boundary, but just a Lipschitz metric, then all you have to do is you have to make the method work for these kind of coefficients, and that's actually possible. So Lipschitz turns out to be the minimum regularity that I need to make this work. Okay, and then finally, I'd like to say something about Schrodinger operators. So actually, I'm more interested in Schrodinger operators than just the Laplace Beltrami on a manifold. So I want to add some potentials. And also you could do this on Rn, you could do this for Schrodinger operators on Rn, with the caveat that you have to stay away from the so-called turning points. Otherwise, again, this method that I use doesn't work at turning points. But in this case, there is also a way around. So you can use a certain multiscale analysis. You can rescale until your operator becomes of the form that you can apply the theorem to. But okay, so on a manifold, everything is much easier in a compact manifold. And actually, I'm not the first to consider this. This has been considered. This has been very well studied recently, in particular by Blair, Sear, and Sock, and also together with Wang in one paper. And so basically what they do in a short sketch is that, assuming that you have spectral cluster and resolvent estimates for your Laplace-Beltrami operator, they can prove that this is stable if you add a potential. So you can get corresponding estimates for the Schrodinger operator. And what my method sort of does is it just uses this as an input. It gives this for free. So it goes like this. Okay, but to be fair, I have to say that they consider a larger range of exponents. So in particular, they don't look just at self-dual inequalities. So here I always look at self-dual inequalities from LQ prime to LQ, but they also look at inequalities from LP to LQ, right, where P is not Q prime. And the method I'm describing here doesn't work for this. It only works for self-dual estimates. Okay. And now I'd like to say something about the resolvent estimates. So I have to start probably with the prototypical result that motivated everything that followed. And this was a paper of Cuenin and Sock from the 80s. So this is the Euclidean version here. We're in Rn, not on a compact manifold. And then you have much better estimates. You have much better estimates than on a compact manifold because your spectrum is absolutely continuous. You don't have any eigenvalues. And so a simple version of this Cuenin-Sock bound is just saying that the resolvent, so there's a uniform bound for the resolvent say if set is of modulus 1, right? And then you get the whole range of set just by scaling because you're on Rn. So this restriction can easily be removed by scaling. And they call these bounds uniform Sobolev inequalities because for the Sobolev case, Sobolev exponents, which is 2n over n minus 2. So here we are in dimension at least 3, and Q prime is so it's plus, no, it was okay. And plus 2, right? So you're on the Sobolev line. In this case, if you do the scaling, then you still get 0,1 on the right-hand side. So it's uniform. So the sigma in this case, not the sigma, but the 2 sigma q minus 1, which enters in the resolvent bound, is equal to 0. So that's why they called it uniform Sobolev estimates. Okay, and this bound actually implies what's called the Stein-Thomas inequality in harmonic analysis. So just as I described at the beginning how the resolvent estimate implies a spectral cluster estimate, this Euclidean version implies this Stein-Thomas estimate, which can also be written as a spectral cluster bound. So Stein-Thomas in the spectral cluster form right, so in the Euclidean case, eigenfunctions of the Laplacian generalized eigenfunctions are just plain waves. So we're just dealing with the Fourier transform basically. And so in this case, I can write projection onto frequencies between lambda and lambda plus epsilon, and I could take lambda equal to 1 by scaling, but I'm just keeping it here to make the connection to the previous estimate from L2 to LQ. And this is going to be, well, not right. It's not, because it's scale invariant. I should better write it like this. And then what we gain is this epsilon, square root of epsilon. And this is true for any epsilon, say, between 0 and 1. Right, and then what the Stein-Thomas theorem says is basically a version where you send epsilon, you divide by 1 over epsilon to the 1/2, and you send epsilon to 0, and you get a restriction operator, or an extension operator, which restricts the Fourier transform of your function to the unit sphere. Okay, so if you can control this by the right power of epsilon, then you can immediately get the original Stein-Thomas theorem. Okay, so back to compact manifolds. So this was first done by Dos Santos Ferreira. I'm going to abbreviate this because it's a long name. Koenig and Salo in 2014. So they asked, can this uniform resolvent estimate from the Euclidean case, can this hold on a compact manifold? And what they found is exactly, they proved 2. They proved 2 for the Sobolev exponent, so q equal to 2n divided by n minus 2. And they asked whether this region, this parabolic region that I showed you, remember the region where we can have uniform resolvent estimates was something like this, was the outside of this parabola. So they asked the question whether this is optimal or whether it can be improved. And just a bit later, in 2015, Bourgain, Sock, Shao, and Yao, they confirmed that this is actually sharp, and they gave a different proof. They gave a different proof, and they also proved estimates on manifolds where you have these improvements, like what I mentioned when you have, for example, if you have negative curvature, then you can improve by a log, or if you are on a torus, then you can use Bourgain's estimates, and you can improve by a polynomial, by a power of lambda. But in general, it's sharp. So it's sharp on the sphere, for example. This region cannot be improved for the sphere, and actually for any Sol manifold. So Sol manifolds are manifolds with plenty of periodic geodesics. Okay. And then, as I mentioned at the beginning, there were several papers who gave different proofs of this. And so let me mention Frank and Schimmer, 2017, and Burke again, Dos Santos Ferreira and Katja Krupčík, about the same time, they proved this for the Steinte mass exponent. So let me call it q equal to 6, right? In 2 dimensions, it's q equal to 6. So if it turns out that if you can prove it for this exponent, then everything else will follow just by Sobolev embedding. So this is more, this implies that the previous bound, this implies this estimate for the Sobolev exponent. Okay, and then there was also work on other operators. So if you look at higher order elliptic operators on a compact manifold, then you can prove similar things, but you have to assume something in addition, namely you have to assume a certain curvature condition that is automatically satisfied for the Laplacian. And this was done by Ullmann and Krupčík. So they considered something like minus Laplace to the power n. Okay, and all these works, they used parametrices, either explicitly or implicitly. So the only work that doesn't use it explicitly is this paper of Frank and Schimmer, but they used the results of Dos Santos, Ferreira, Koenig, and Salo. They used the bounds on the Hadamard parametrics for their argument. So they also use parametrices in some way. Right. So in the original paper here, the 2014 paper, they used the Hadamard parametrics for the resolvent, and then in the later paper of Bourgain, Sock, Shao, and Yao, they used the Hadamard parametrics for the wave equation. And then Burke, Dos Santos Ferreira, Krupčík, they used the semi-classical WKB parametrics, and Ullmann and Krupčík used what's called the Lax-Hermander parametrics. So they all used parametrices, and these estimates can be quite complicated. And so the result that I'm describing here doesn't mention parametrices at all, not in a single step. It just takes the spectral cluster estimate, and everything is encoded in the spectral cluster estimate. So the whole geometry is basically hidden in the spectral cluster estimate, and you get the resolvent estimate more or less for free if you have this black box thing. Okay, so to conclude, let me state the main new results. So the first result, as I said, is basically that 1 implies 2, spectral cluster implies resolvent. Of course, we have to assume some things. So let MG be a compact Riemannian manifold without boundary, as I said, but you can get the boundary case by using this trick of Smith and Sock. And in this case, you want your metric to be at least Lipschitz. Okay, and then you have some restrictions because of Sobolev embedding. You have to restrict to Qs that are below the Sobolev exponent. Okay, and then if you have this, then indeed one spectral cluster implies resolvent estimates. And the second result concerns perturbations of the first result. So let me call this stability. So the advantage of the resolvent estimate is that it's very stable on the perturbations, because you have the resolvent formula and you can easily add in perturbations. You cannot do this directly in the spectral cluster bound. So if in addition your potential is you can have a singular potential in Ln over 2, right? On a compact manifold, because it's compact, n over 2 is the largest class. Ln over 2 is the largest class. If I have a p which is bigger than n over 2, then LP of that will be included in Ln over 2. So this is the most general condition here. Okay, then the spectral cluster bound for the free operator, not for the perturbed operator, actually implies spectral cluster and resolvent bounds for the perturbed operator. In the same range of Qs as above. Okay, so you don't get the complete spectral cluster bounds for the Schrodinger operator. You only get it up to the Sobolev exponent because you're using this this resolvent to pass through the spectral cluster bound. And actually, in these other papers of Sock, Huang, Sear, they obtain a larger range of Qs. Okay, I'm not going to go into the proof. I intended to explain a little bit how the proof goes. The proof is very easy. Let me just say in words that what you do basically is you factorize. You factorize. So the proof idea is just the factorization. It's a factorization that, let me do it for constant coefficients because then it's completely explicit. I don't need any pseudo-differential operators if I have minus Laplacian on Rn minus lambda squared. Right, what I do is I go to Fourier space, I write the symbol of this, and then I factorize. I write this as xi1 minus the square root of lambda squared minus, let me write xi square here. So I go to Fourier space, and let me denote all other variables xi2 up to xin by xi prime, and then I just factorize it like this. Same square root here, and to do this I have to localize in frequency. So I have to localize to a cone here. If this is the xi1 axis, I have to localize to a cone, and since I'm only interested in the characteristic set, I can just restrict myself to a small slab inside this cone here, right? And then I just use a partition of unity. I put together all these cones, and this just costs me a factor, a constant depending on the dimension. But when I do this, then I can basically forget about this, because in this set and in this regime, that's an elliptic operator, and it's basically of order 1. It doesn't do anything to the estimates, so I can restrict myself to this thing here, and then I have a first order operator, and I view this as a hyperbolic operator. So I consider x1 as a time variable and x prime as all the other space variables. And if you do this, then you can use what is called the Christ-Kisselev lemma, which basically tells you that if you have an estimate on an integral operator with a kernel, then you can localize this estimate. The same estimate is true up to a constant for the kernel where you truncate. You truncate to a smaller time interval. So basically, the idea is to use this Christ-Kisselev lemma, but you have to use it at the right place. And this factorization and this interpretation of x1 as the time exactly gives you the right setting for this. So yeah, that's it. Thank you very much.
Thank you very much. Do we have any questions for Jean-Claude?
Can I ask a question about your stability theorem, theorem 2?
Sure.
You said that this holds for the exponents that you have in the theorem 1.
Yes.
I didn't catch whether you say it only holds for those ones, or it's only proved for those ones?
So the resolvent estimate is only true for this one, because you have to, the resolvent estimate cannot be true if Q is bigger than the Sobolev exponent, because the elliptic estimate fails.
Okay.
So in this case, it's completely sharp. But the spectral cluster bound, there's no reason that you can only go to the Sobolev exponent.
Okay, I can't immediately see why you can do better for the clustering estimate.
Well, for the cluster estimate, what you can do is basically you should be able to go to higher Q. Maybe not all the way up to Q equal to infinity if your potential is very singular, but you should definitely be able to go to higher Q. And in this paper of Sock and Sear and so on, they obtain these kind of results.
Okay, thank you.
So it's a limitation of the method that you cannot go past this Q for the spectral cluster bound.
Thanks.
More questions?
Can I ask something? How essential in this is it that you have a Laplace-Beltrami operator on a manifold? I mean, are there similar results for, say, Schrodinger operators,
yes.
which also have
yes.
a purely discrete spectrum?
Yes. It's not essential at all. Basically, what you need is, I mean, if you have a pseudo differential operator, and your symbol is of principal type, which means that if P vanishes, then this doesn't vanish. Then you can do it. And so this includes the case of Schrodinger operators. But the problem is, for example, if your P is say minus Laplace plus X, the harmonic oscillator, and then you look at the eigenvalues of size lambda squared, then of course when you're at the turning point, then this condition fails, right? If you're here, then the condition fails, right? If I write this xi squared plus x squared minus lambda squared is 0, and x is lambda, then xi is 0, so the xi of the symbol is 0. So at the turning point, this condition fails, but there are certain multi-scale methods that you can use to rescale the thing. And once you go incrementally to this turning point, and in sort of dyadically, and in each dyadic region you rescale the whole thing so that your d psi p becomes again of order 1, and then you can apply this method. But it's a bit more technical in this case.
Thank you.
Yeah, I also wanted to ask the same question, so I'll just follow up on that. So here, I suppose you assume P to be a pseudo-differential operator of order 2, or any order.
The order is not important. The order always, basically, if you have an operator of order m, then you can factor out m minus 1 powers and basically just as a power of lambda and times something which is of order 1.
Yes.
Right. So imagine that you do this for higher powers of this operator. So you take I don't know, you take psi to the 4 minus lambda to the 4, and you do the same thing, and then
say, but what about fractional powers? Say,
fractional powers can also be dealt with.
Mm-hmm.
They can be dealt with, but it's a bit more technical. But actually, I have a result in the paper about the fractional powers. So for the fractional Laplacian, even for the fractional Schrodinger operator, so something like this can be dealt with.
Mm-hmm.
Where alpha is say between 0 and 2.
Mm-hmm. I see. So you don't need any positivity of the operator for higher
No.
or they're pseudo-differential?
No, not at all.
I see. And what about non-scalar operators? Say if you want to deal with systems.
That's probably more difficult because just because of the commutator
Yes.
what I use is that if I do this factorization here, and if my operator is a pseudo-differential operator, then of course it's not true as written. It's not a true formula, but I get sort of an error term.
Yes.
And this error term will be one order better than the main term. But if I have a system, then I think there might be a problem with the commutator might not be one order better than the main term.
Mm-hmm. So, and if anything is known for systems in general?
I don't know. I mean, I've done Dirac in the Euclidean case, but what you do for Dirac is basically you reduce it to a scalar problem. Because if you write the resolvent of the Dirac operator, it's like applying applying the first derivative once to the Laplace resolvent, and then it's completely analogous.
I see.
So I don't use any special structure of the system, but that is an important point. Maybe for systems this could be more challenging for more general systems, not for Dirac.
Mm-hmm. Okay, thanks. Any more questions? This doesn't appear to be the case, so let's thank our speaker again for the very nice talk.
Thank you.
And let's adjourn to next week for the last seminar before the summer break. So.